You ever see one of those crazy long chemical names and just think, nope, that's a secret code? You know, with all the numbers, the hyphens, the words that sound like they're from another planet? Well, what if I told you it's not a code meant to keep you out, but a language designed for absolute, perfect clarity? Today, we're going to crack that code together. Okay, so let's start with a really simple example. On the left, we've got acetic acid. You definitely know this one. It's the stuff that gives vinegar that sharp kick. But on the right, you see ethanoic acid. That's the official systematic name for the exact same thing. So, why? Why have two names for one molecule? This right here is the heart of the problem. When you have multiple names, you get confusion. And in science, confusion is a recipe for disaster. So here's our game plan for today. First, we'll see what things were like back in the chaotic, early days of naming. Then we'll meet the international group that brought order to all of it. After that, we're going to take a deep breath and decipher a ridiculously long chemical name. I promise it's not as bad as it looks. Then we'll see how those same complex rules are built on really simple foundations. And finally, we'll talk about why this whole system is just so important. All right, let's step back in time a bit. Before we had this organized system, naming chemicals was, well, it was basically the Wild West. It was a total free-for-all with names that were inconsistent, regional, and honestly, not very helpful. And this is the key right here. A lot of these old-school common names just came from wherever the chemical was first discovered. For instance, formic acid gets its name from formica, which is Latin for ant, because, yeah, scientists first got it by distilling ants. Seriously. Acetic acid comes from acetum, the Latin word for vinegar. Now, that kind of worked when we only knew about a few hundred compounds, but it's a system that just can't keep up when you start discovering millions of them. And that right there is the huge challenge. As chemistry just exploded as a field, we needed a much better way. A system that could give every single possible organic molecule its own unique logical name. A name that anyone, anywhere on Earth, could use to draw the exact same structure. I mean, how do you even begin to do something like that? Well, the answer came from this massive international effort to create a single universal language for all of chemistry. And it was all spearheaded by an organization called UPAC. IUPAC is a bit of a mouthful. It stands for the International Union of Pure and Applied Chemistry. They got together and created a system, a set of rules for naming molecules. The goal was huge, but simple. One official, systematic name for every single compound. No more confusion. Acetic acid has its place, but ethanoic acid is the single, universally understood name. And this is the really beautiful part. The core idea is that an IUPAC name isn't just a label you slap on a bottle. It's a precise set of instructions. It's a step-by-step recipe that tells any chemist in the world exactly how to draw the molecule, atom for atom, bond for bond, with zero ambiguity. Okay, time for the main event. Let's see this language in action. We're going to take a look at a really long, really intimidating name and just pull it apart piece by piece. Don't worry, it'll make sense. Okay, deep breath. I know. This looks like absolute nonsense. It looks like somebody fell asleep on their keyboard. But I promise you, this isn't random at all. It's a perfectly logical set of instructions. And by the time we're done here, you're going to see just how elegant it is. Believe it or not, this entire system, no matter how complicated the name, just boils down to these 4 basic steps. First, you find the molecule's backbone, the longest chain of carbons you can. Then, you spot all the important bits and pieces hanging off of it. Third, you give every carbon in that backbone a number, like a street address, so every piece has a location. And finally, you just list all those pieces in alphabetical order to build the final name. Okay, let's start decoding our monster name. See that part right near the end? Tricosa? That one little word is the root of the whole thing. In the language of IUPAC, tricosa means 23. So just like that, we know this molecule has a backbone that's 23 carbons long. Boom, we've got the skeleton. Now let's look at the very end of the name. Di3-9-dione. The "one" part tells us that the most important type of attachment here is something called a ketone. The di tells us there are 2 of them. And the numbers? Well, those are their addresses. They're attached to carbon number 3 and carbon number 9 on that 23 carbon chain. See, it's all starting to click into place. So what about all that stuff in the middle? Well, that's just the rest of our recipe. It's an alphabetized list of all the other ingredients attached to the main chain. We've got a bromine atom at position 18, a butyl group at 12, a chlorine at 11. You see the pattern? Every single piece has a name and a number telling you exactly where it goes. And here we are. That terrifyingly long name isn't terrifying at all. It's an exact recipe, a blueprint. Following these instructions, any chemist anywhere in the world can draw the exact same, really complex molecule with no mistakes. The code is officially cracked. Now that was a huge example, mainly to show you how powerful the system is. But the real beauty of it is that these same rules are built from really simple, logical pieces that apply to chemicals you might actually have around the house. This right here, this is like the alphabet of organic chemistry. These prefixes tell you how many carbons are in the main chain. 1 carbon is meth, 2 is F, 3 is prop. This is the absolute foundation. And hey, remember ethanoic acid from the very beginning? That F prefix was our first clue. It told us right away we were dealing with a 2-carbon molecule. So let's see how this works. It's super simple. You take a prefix for the chain length, like prop for 3 carbons. Then you add a suffix for whatever the main feature is. For an alcohol, that suffix is -ol. Put them together and you get propanol, the main ingredient in rubbing alcohol. Easy as that. Let's do one more. The prefix for a 4-carbon chain is but. If that chain has a carbon-carbon double bond in it, the suffix is -ene. You just snap them together and you get butene. It's literally like chemical Legos, where each piece has a specific shape and function, and you just click them together based on the rules. Okay, so let's zoom back out. We've seen how the system works, from the simple to the complex. But why is having this universal language so incredibly important for science, and really for all of us? Before IUPAC, global science was kind of messy. Researchers in different countries might use totally different names for the same exact compound, which led to all sorts of confusion, wasted time, and duplicated effort. After IUPAC, we get clarity. A scientist in Tokyo and a scientist in Buenos Aires can read a chemical name and know with 100% certainty that they are talking about and working with the exact same stuff. So here's what it all boils down to. This system gives us a language that is first, completely unambiguous. One name, one molecule, period. Second, it's descriptive. The name is the structure. Third, it's global, a shared language for all scientists. And maybe most importantly, it's logical. It's based on a set of rules, not on trying to memorize millions of different names. It transforms chemistry from just a collection of facts into a system anyone can learn and build upon. And that leaves us with a pretty big final thought. By doing this, chemists created more than just a naming system. They created a perfectly logical, even machine-readable language for the physical world. This system is the backbone of huge chemical databases. It powers AI and drug discovery, and it ensures safety in labs and factories worldwide. So if we can do this for molecules, what other complex systems out there, in technology, in society, maybe even in our own biology, are just waiting for us to invent their own universal language of absolute clarity?